Hello everyone. Consider the lab equipment with a top-down view that we are going to use quite a bit in part 2 of the rotation unit. Now, we've seen this equipment before. It's a bar with a couple of masses. It's attached to a very, very low friction rotary motion sensor that can measure rotations. In the first part of this unit, we saw this equipment and we found a model for constant angular velocity when it rotated constantly. Right? Some new math models, some new variables, some new terminology. This time it's going to be a little different. So watch what kind of motion this has. Did it look constant? Yeah, it looks like it's speeding up, right, as it spins counterclockwise. So the angular velocity is not constant here. Right? The angular velocity is changing. And I know we have a word for that, which will turn into rotation terms in just a little while here. So what might you expect the angular position in radians versus time in seconds graph to look like? After all, it is spinning faster and faster as it goes. Well, hopefully you're saying, well, I know what that would look like linearly, so maybe it'll look the same. A top opening parabola. Because remember, the slope of a tangent line on a position time graph, or an angular position time graph, is the angular velocity. And if the angular velocity is increasing, the slope has to get steeper and steeper. Well, we've seen lots of top opening parabola relationships in here. What do we have to do to linearize it? We have to square the time. Right? So if we graph angular position in radians versus time squared in seconds squared, we will get a linear graph that goes through 0, 0. Hence, we can say that for this type of motion, the angular position is proportional to the time squared. So if allowed to rotate for twice as long, it'll have moved through 4 times the angular position. If we allow it to rotate 3 times as long, it will reach 9 times the angular position. Right? Angular position proportional to time squared. And yes, this is just like what we saw, right, in another unit linearly. Right, so let's keep that in mind. Okay, so it acts a lot like the carts rolling up and down the inclines, right, that we used in honors. So what would the angular velocity versus time graph look like? Well, if this is the simplest kind of speeding up we could do, right, like the cart going up and down the hill, we would get an angular velocity in radians per second versus time graph that was a linear graph that went through 0, 0. Notice that it is changing, but it is changing constantly. There's a linear change to it. And since the graph is linear and contains 0, 0, the angular velocity is proportional to time. And of course, we can make a math model out of this. Right? The y variable is the angular velocity. That's going to equal the slope, whatever that is, in units of radians per second. What would that mean? Well, if we turn this into a for every statement, for every second, right, the angular velocity changes by this many radians per second. It's how quickly the angular velocity is changing. Right? Not how fast it's rotating, but how fast it's rotating faster. And yeah, we have a name for this. We'll give it to you in just a moment here. Sounds a lot like a linear quantity we have, right? How much faster we get faster. We can also reduce these units, right? And so we get radians per second squared, right, as the reduced units. A little hard to interpret what they mean, right, with that, but that is the way we tend to write the units because it's just more compact, easier to write. The x variable is the time, and the y-intercept is 0 because it started from rest. So we are going to call this slope the angular acceleration. Just like the slope of a linear velocity time graph is the linear acceleration, the slope of an angular velocity time graph is the angular acceleration. And this is alpha. All right, alpha. Lowercase alpha, by the way, for acceleration, I guess. So this is the slope of an angular velocity versus time graph. Well, if we want to turn that into symbols, of course a slope takes 2 points. And you find the slope by doing rise over run. In this case, the rise would be how much the angular velocity changes. And the run would be how much the time changes. So, if the angular acceleration is the slope of this graph, we can say the angular acceleration is the rise, the change in the angular velocity, over the run, the change in the time. Or in more mathematical language, this is the rate of change of angular velocity. It's how quickly you're speeding up, slowing down, or changing direction. Angularly. Right? And yes, when we look at more complex cases, right, than this, we'll have to use a derivative for this. So one more step to make this a little bit more useful, a little bit more general. What if instead of starting from rest, what if at 0 time we already had an angular velocity? Well, hopefully by now you're good with what we're doing here. This would just mean, since this is a graph of angular velocity versus time, if at 0 we were already moving, we would have a y-intercept. Wouldn't change the angular acceleration, wouldn't change how fast it got faster. Right? That would take a change to the equipment, which is something we'll investigate later on. But it would end up with a y-intercept. So the y-intercept is just your angular velocity at 0 time, which we are going to call omega sub o, which is, of course, your initial angular velocity. So just as we do with linear kinematics, final has nothing as a subscript, and initial has an o for 0 or original, I don't know, but that's just how we write it. So omega sub o is the initial angular velocity. So creating a little more general math model of this, the y variable is the angular velocity. That equals the slope, but we just decided that the slope of an angular velocity versus time graph is the angular acceleration. The x variable is the time, and the y-intercept, we now know, is the initial angular velocity. Since this is addition, we can flip the order, it's commutative, and we get this equation. And this is an equation that relates the angular velocity, the initial angular velocity, the angular acceleration, and the time to one another. 4 variables. But notice it's still for a very special kind of motion, because our angular velocity time graph is linear. And linear graphs have what kind of slopes? Constant slopes. And since the slope of this graph is the angular acceleration, this is an equation that describes uniform angular acceleration. Now, if you're following this, right, and especially if you're putting this into context with the linear analogy, you're probably saying, oh, that looks a lot like the first kinematic equation. V equals V sub O plus AT. And it is, really. It's just a rotational kinematic equation. And I'm not going to redo the math, right? But if we looked at the areas under the curve here and did some other things, we could come up with a set of 4 equations which describe uniform angular acceleration. And those are the rotational kinematic equations. See how it rotates on its way in? Rotational kinematic equations. Final angular velocity equals the initial angular velocity plus the angular acceleration times the time. Second kinematic, angular displacement equals 1/2 times the sum of the final plus initial angular velocities times the time. Remember, this one is really just displacement is average angular velocity times time, because with uniform angular acceleration, the average velocity is just the initial plus the final divided by 2. It's the middle velocity. Right? The ever-popular third kinematic equation, angular displacement, equals the initial angular velocity times the time, plus 1/2 the angular acceleration times the time squared. And the fourth kinematic equation, final angular velocity squared equals the initial angular velocity squared plus 2 times the angular acceleration times the angular displacement. If you were to look on the equation sheet for the APC test, right, which you are allowed to use on tests, both in here and the actual AP test. As with the linear kinematic equations, it only lists equations 1, 3, and 4. I guess it assumes you should just know this one, as displacement is average velocity times time, linearly or rotationally. So it does give you the first, the third, and the fourth. You just have to know what all the symbols mean, right? And so we're going to practice a bit with doing these, but really, it's going to be the same method. You know, when we come up with something which we know as uniform angular acceleration, right, we can decide what is it we're looking for, what are we given in the problem, and then that will help us pick a kinematic equation. Because just like the linear cases, each one is missing something. The first one, nothing about the angular displacement. The second one, nothing about the angular acceleration. The third one, nothing about the final angular velocity. And the fourth one, nothing about the time. Right? If time is not one of the variables, or what you're looking for, only can use the fourth one. So I'm hoping that you can convert over, but it is a little harder, right? Because it's rotating and you got to be careful with units and all that kind of stuff.